Welcome, ladies and gentlemen. This is our second video on integrated rate law, the third video overall in our kinetics unit. In this video, I'm going to be talking about the integrated rate law for zero and second order reactions, specifically essentially how they relate to the integrated rate law for first order reactions. So we're sort of putting it all together, looking at it for the other orders, and then looking at it for zero, first, and second all together. So first up, integrated rate law for second order reactions. We're going to talk about second order first and then go back to zero order. As a reminder, basically, what do we know about second order reactions? We know that by definition, the rate of a second order reaction depends on the concentration of a reactant squared, or overall, you can get a second order reaction by having two first order reactants. So we kind of have these two options. Is it one reactant squared, or is it two separate reactants but directly? Similarly to our integrated rate law for first order, we know that rate by definition, again, this right here is the definition of rate. It's true regardless of order. Notice it's the same as that for first order. Rate is the change in concentration of A over the change in time. And we know, again, and here's our rate law, right, that rate is equal to K times the concentration of A squared for second order. So this is what we know is true about second order. Again, using our magical calculus, it's not really magical, we're integrating with respect to initial and final concentrations of A, and with respect to time, we can get this equation, which is our integrated rate law for second order reactions. Notice this is different than our integrated rate law for first order reactions. We have a different relationship here because of the fact that, it's second order rather than first, so we have a different power that we're using. 1 over the concentration of A at time t minus 1 over the concentration of A at time 0 is equal to KT. And here I've simply rearranged it ever so slightly by adding 1 over the concentration of A at time 0 to both sides, because just like with the integrated rate law for the first order reaction, if I do this slight bit of rearrangement, now I have a pattern that looks like y equals mx plus b, where this bit right here is y, this is mx, and this is b. This is critical because now this is in slope-intercept form. This is a straight line. If you have a second order reaction and you graph 1 over the concentration versus time, you get a straight line. A straight line will result from that graph, and that is a huge point because this is how we can determine if something is second order using a different set of data than the method of initial rates. When we do this, when we make this graph and we get the straight line, the slope of the graph will be equal to K. Just like if we do integrated rate law for first order and we graph natural log versus of concentration versus time, the slope is equal to the absolute value of the slope, I should say, is equal to K, or the slope is equal to negative K. But again, we have that slope coming in, that slope, the thing that is not changing, is going to be our rate constant. And the y-intercept will be 1 over the initial concentration of A. So things that are true about second order reactions. This is essentially summing up everything that is true about second order reactions. We have the fact that rate is equal to the change in concentration of A over change in time. This is just the definition of rate. It's true for all reactions regardless of order. This is our rate law right here. And then the new one that we're introducing, this is our integrated rate law. This equation is on your reference table, which is very nice of them. It actually didn't used to be. You used to have to memorize the integrated rate laws, which is very mean of them, but they've changed that, so that's very nice. And half-life, because we still have half-life with second order reactions. Now, these equations for half-life are not on your reference table, so you don't actually need to know them. We're not going to be doing that much work with them, really any work with them. I'm just letting you know that basically this equation for half-life is not the same as it was for first order. And notice that we do now have a dependence on the initial concentration. So now with second order things, half-life is not the same regardless of your initial concentration. It does matter how much you're starting with. That's a big shift from first order half-life problems. And then looking at our graphs, concentration versus time, natural log of concentration versus time, 1 over concentration versus time. For a second order reaction, it is not concentration versus time that gives you the straight line. It is not the natural log of concentration versus time that gives you the straight line, but it is 1 over concentration versus time that gets you the straight line. And that is huge. This is a huge point that the AP actually loves to ask about. Basically, when does which order get you a straight line? And knowing that it's natural log versus time is going to be first order, and 1 over concentration versus time is going to be second order. Now, zero order. What is true of zero order reactions? What is the integrated rate law for a zero order reaction? Well, once again, we know that the zero order reaction does not depend on the concentration of the reactants at all. So this is our definition of rate. This is our rate law for zero order. And then this right here is our integrated rate law for zero order reactions. This is actually not on your reference table. You wouldn't really have to do that much with it. I am going to ask you a few questions about this on our in-class problem set, but you can look up this equation from the notes and use it there. Know, however, that I probably wouldn't ask you anything with this formula on the test because it's not on the reference table, and the AP certainly wouldn't ask you anything about that. Again, a comment on half-life. Oh, let's go back. Half-life for zero order. Once again, notice we do actually see a dependence on half-life with concentration. This is not on your reference table. You definitely don't need to know that. But the big point, when does which graph get you a straight line? For zero order, it is not natural log of concentration versus time where you get a straight line. It is not 1 over concentration versus time that gets you a straight line. But now it's concentration versus time, just on its own, not having to do anything else. That gets you the straight line. And once again, because this right here, you can rearrange this to get this into slope-intercept form, the k value will be the absolute value of the slope. Notice the slope is negative. K won't ever be negative. K will always be positive. So you're always, in essence, taking the absolute value of that slope. Summing up basically what we know to be true about these three integrated rate laws and putting them all on one page. We have zero, first, and second order. We have what the rate laws look like right here, the distinction in rate law between zero, first, and second order. And then we have integrated rate law for each one. Sometimes I refer to this as the concentration and time because this is now a formula that equates the concentration of a reactant to how long it takes for that concentration to change. And it's different for every order. These two are on your reference table and you will be expected to use them. And then half-life as well. What I do want to point out about these, all the integrated rate laws, you can rearrange all of them to be y equals mx plus b. So they're essentially telling you when is what a straight line, and it's different for each order and for each case because they are essentially in slope-intercept form. K is going to be equal to the absolute value of the slope for each one. So that's how we can get the value of K graphically for each individual order. So I'm not going to go through this question, I'm not going to solve it, but I do want to show it to you and talk about it a little bit. So we have this problem here, this new kinetics problem. The following data were obtained for the gas phase decomposition of nitrogen dioxide at 300 degrees Celsius. Remember, you're not actually doing any math with the 300 degrees Celsius. It's sort of just there to tell you that whatever rate constant you might be using, that's going to be valid for that temperature only. And we have the reaction, and then we have the question, is the reaction zero, first or second order in NO2, and how do you know? We'll look at the information that's been supplied to you. Other than the reaction, other than the temperature, we have this chart right here. And in this chart, they have given us time and concentration. This is not, this data table, this is not 5 separate trials. That is not what this is. This is not our method of initial rate where they did trial 1, trial 2, trial 3, changed the concentration of NO2 in each trial and measured the rate. Notice this is a totally different data set. This is only one trial. And they've simply monitored the concentration of the NO2 with respect to time. They're measuring the concentration of the NO2 at different time periods. This is not the method of initial rate. This is not 5 separate trials. This is just one trial, and we're simply monitoring it. So you can't say, okay, well, let's look at, trial 3 and trial 2 and see how the rate changed. There is no rate. Not in this case. The only way to work out the order for the reaction, because you're definitely not going to get it by looking at the balanced equation, right? That's not going to tell you order. The only way that we can tell what the order is to take this info that's in this table and graph it. We have to graph it. But you have to make not just one graph, you got to make 3 graphs. You got to make 3 graphs. And the 3 graphs that you're going to make are going to be the 3 graphs for the orders that we've been talking about. So we want to graph concentration versus time. So we'd want our first graph would be the concentration of NO2 versus time. So just the information that's in that chart right there. And that's it. Then we want to take the natural log of each of the NO2 concentrations that are here and graph the natural log of concentration versus time for our second graph. And then for our third, we want to do 1 over the concentration of NO2 versus time. What we're looking for is which graph gives us the straight line, because only one will give us a straight line, and whichever one, that's going to be how we're going to figure out the order. If we get the straight line, so let's say I'm just going to add that in, look for the straight line. If this one gives us the straight line, looking like that, then we know the reaction is 0 order. These are our axes, concentration versus time, where if we get a straight line, that means 0 order. If we graph it here and we get a straight line, that's what that's showing, then it's first order. Natural log of concentration versus time, that's first order. That's where we get the straight line. If we graph that, 1 over concentration versus time, and we get a straight line, this one actually increases, then it's second order. That's how you have to deal with this set of information, right? Concentration and time for only one trial, and that's all we have. We don't have a rate constant. You have to work it out this way and say, okay, well, which set gives us the constantly decreasing or constantly increasing data? So that's integrated rate law. And you'll be looking at problems that sort of deal with this idea of different graphs and different axes, and some questions with the integrated rate law for 0 and second order on Tuesday.